Okay,
I can start.
welcome everyone. I'll give you a short introduction. It's my pleasure to introduce today's speaker to this CDAC webinar, Christian Tantardini from King Fahd University. He's actually joining us from Lake Como in Italy, where he lives, or where he's from. Christian is a theoretical computational chemist slash materials physicist who has worked on a variety of problems that include materials in extreme environments. He obtained his bachelor's in chemistry and industrial chemistry at the University of Insubria and a master's in chemistry at the University of Milan. He then obtained a PhD in material science and engineering at Skolkovo, working with Artem Oganov. He also has had appointments in Novosibirsk, the Arctic University of Norway, and Rice University. The work he did with Oganov led to a very highly cited paper on the thermochemical electronegativity of the elements. He's also worked on a variety of problems associated with computational methods, as well as applications not only in extreme environments, but also in high entropy systems and 2D systems, which I think he'll tell us about today. So welcome to this webinar. We're looking forward to your talk.
Thank you so much for the invitation. So today I will talk about this very exotic state for antimonium and how impact in the environment to stabilize this state and how it can be useful for electronic device. I will introduce a little bit myself. I am a research assistant professor at the King Fahd University. I also was granted by Alexander von Humboldt Association for my work on the excitons. So my focus research, simply to make clear what I'm doing now, is about excitons and specifically to find a new numerical solution for the Bethe-Salpeter equation. And I one of the main developer of Abinit code. I also interested in Clifford algebra specifically to rewrite as part of the current language for spin, topology, symmetry, and theory response using quaternions and also octonions. I'm collaborating with Nicole Fouret, part of my work. Here at the College of Petroleum Engineering, I also started a new part of research about fluid dynamics and specifically I assist in the multiscale modeling to look how in the porous media the multi-flow, multi-component can actually work. And specifically, I am also interested in radiation shock materials. So actually, I use this code Flash from the Rochester University in US to actually study the coupling between radiation and shock, because we have a classical and non-classical part that are coupling together. So this is my interesting. So today I will start to introduce the broad question that is about how the environment can affect the material. If we think that we have materials and different materials are not simply defined by only the composition, but at the different level of the matter that we are considering, the environment like temperature, like pressure, and could really affect in a different way. For example, in the atomic scale, we can see that the bond lengths, the orbital overlap, they actually can affect the valence, the chemical bonding, and specifically can affect actually the electronic properties. In the nanoscale, specifically when we make this confinement in 2D, when we move from 3D to 2D, we see that the termination, the functional group, they can affect also the electronic structure and the properties of the material. This is true also when we grow up in the mesoscale and macro scale. If you think that we have porous media, it's interesting to see that specifically these polydispersed material, they change a lot based on how the dispersion of the grains or how the pores are distributed. And in macro scale, we know that if we have different materials that we use every day, will be affected by transport and like charge or heat transport. So in particular today, that what we will be interested in the atomic scale is about that we have a surface termination, so actually the local chemistry of the confinement of in 2D affect the electronic states, and so the properties of the material. Also the pressure, for example, the pressure on 2D materials, we can think at uniaxial pressure along the z-axis if we think that our material is spread on the xy surface, that will be affect the chemical bonding and also the properties. And specifically, we see that the confinement on 2D materials modify the electronic structure of the material that can be acted totally different, and also the thermodynamic, and we can also discover new phases. My previous work done on this kind of materials that actually was one of these work was the prediction of a new hexagonal and synthesis, because we worked also with experimentalists, that we have got this new hexagonal to the hexagonal sodium chloride. Also, we have worked, for example, in high pressure, and this was a developing of the CODA beneath to model the uniaxial pressure, doing actually introducing this stress tensor and be allowed to have not hydrostatic pressure only. And we have looked that the silicene can be a possible field effect transistor. So that changing by uniaxial pressure, we change the hybridization of our silicene, and we got new electronic properties. And about functionalization, we have seen with Jakobson at the Rice University that specifically when we have these diamonds, for example, and we change the termination from hydrogenated to fluorinated, we have effect that can be more related like bulk effect or like surface effect. So actually, previous work was done. Today, to make aware everyone of the concept that you will see in this presentation, I will introduce for the people that are not aware about what is quasi-particle. If we think quasi-particle in a strict way as was introduced by Landau, we see that we have many particles in a material, and when happen an excitation, this perturbation actually create a collective excitation, and then actually these excitation move through the material and we call quasi-particle. So it's not a fundamental particle, but an effective particle that simplify the description of in the many-body system. We can really also simplify if you are swimmers and you swim, you see that when the swimmer go straight, there are waves around him. So he's creating a perturbation. And these waves plus the swimmer can be considered also a quasi-particle. So specifically also I will introduce the word exciton. So, and I will talk about a little bit. So exciton in crystal, we know that affect a lot the absorption spectra, because at the moment computationally, when we have the self-interaction error, that depending by when we use DFT, okay, that affect the valence band and can be removed using quasi-particle approximation, GW. But the formation of exciton, so the coupling between hole and electron that affect and it's called optical excitation and affect the optical spectra, they need to be described by the Bethe-Salpeter equation. So the exciton, simply briefly spoiler about what I'm doing, is actually to rewrite the Bethe-Salpeter using freedom approximation that change this problem and make this problem more numerically possible to solve for also big systems. So introducing this concept, we now see why the low dimensionally are very interesting and attractive. So it's attractive to study perovskite when they are in 2D instead of simply 3D. The first one of the cases is actually that several devices that can be more stable and increase their performance, like for example the Rudolstein-Popper solar cell that actually achieve higher efficiency respect their counterpart, the 3D analogous. The same is actually that when we have 2D perovskite, we see that they are natural quantum wells. So actually, specifically when we have these inorganic, organic layers, they make like actually change the electronic properties and specifically actually allow or not the excitons to be transferred. And the same is when we look, for example, the exciton, the diffusion, they can be also trapped, okay? And the trapping of the exciton can be released by diffusion or subdiffusion. So another aspect of the 2D perovskite that can be very interesting to be studied is actually that the presence of a heavy element. Of course, now we are in a world that we are moving from lead perovskite to non-lead perovskite because we know that we want to have more environmental green world. So, but there are also other heavy elements that can be used successfully, and we can have different effects. For example, we can have a Rashba splitting, and it's easy measured, and we can also have chiral 2D perovskite with the spin polarized photoluminescence without magnetism field. This is very interesting because we can tune the photoluminescence without have the counter effect of the magnetic field. So for this reason, it seems that the perovskite 2D should be interesting to be studied. Specifically, we can think this kind of perovskite where we have written like A2BX6. In this case, it's like that are interesting chemical scaffold where we have these BX6 octaedra. They can be lead-free, and one of these that it's actually the object of our study, it was rubidium-2, antimony, and chloride-6. Antimony is better than lead, but of course is not the most green that we can think. So, antimonium, our specific question was, we have looked in the literature that antimonium in a very old experiment in the 70 or 50 something, were obtained antimonium-4. And it is considered a very rare state because most of the time we know that there is a disproportion and we have antimonium-3 and antimonium-5. Specifically, we wanted to see if the 2D confinement, okay, moving from a bulk state that is already well-known study to give this proportion, go to the low dimensional, we can stabilize the 4, or we can have also a mixed valence, we don't know at the moment, and have band inversion and also spin-orbit transfer because antimony can be responsible for spin-orbit coupling. So about spin-Hall effect, actually, one of the concepts that I would like to introduce, spin-Hall effect come from the spin-orbit coupling. So when we have a current like this, and we have a strong spin-orbit coupling, actually, we will see that we will have a spin current that go one from the up and the other from the down spin. And so we will see that the electrons will be aligned in two different places, making spin up and spin down. So this actually is a simple explanation where spin orbit coupling make a deal. So if we have no heavy element, spin orbit coupling will not be present. It is not true that it's not present, but it is so low that cannot deflect the spin at the current.
Could I ask a question, please?
Yes.
I mean, this was about excitons, and so my question is there a particular rate for exciton in plane and perpendicular to the plane? Are the rates of exciton transfer? I don't know if I'm making sense. I don't even know if it's a valid question.
Can you repeat? I'm sorry.
Does exciton have a particular rate in plane versus perpendicular to the plane?
No, actually the exciton, the problem of the exciton, if we have strong spin-orbit coupling, we are entering for the Vanier excitons, because there are Frenkel and Vanier. The Vanier excitons that we see in solid state, in organic, usually, we see that in strong, if there is a strong orbital spin-orbit coupling, this could actually make this exciton more localized, because we are entering in the place where we have a strong also correlated materials. We see most of them, and they are very localized. So I think that if we have excitons in spin orbit, a strong spin orbit coupling, the deflection of them will be decreased of the spin. So the presence of the exciton will affect the spinel effect. So actually we will see materials that will not be so responsible, because the excitons is a perturbation that decrease your performance. We can make like this.
Thank you.
Okay. So another aspect that I introduced about the band inversion is actually that when we have Kohn-Sham electronic band structure, we know that we lost all information about the orbitals where they come. We know that usually this band, they have a remnant of their orbital, and we see that usually at the gamma, where we have the minimum gap, we have the S-like and P-like that are actually, one is the valence, part of the valence, and the other is a part of the conductivity. It happens that at gamma, when they touch, actually, and they move from gamma away, the reopening of the gap gives an inversion of band. This actually because it's associated to an inversion of these two bands. That is actually is seen in topological insulator that can be whale semi-metal, nodal plane semi-metal. So in this kind of tricky materials that can be interesting. About what that we are looking for the antimonium for, we know very well that there is this Moshauber experiment that confirmed that at the moment what the people see for the bulk, we see that we have antimonium 3 and disproportion. So actually we have antimonium 3 and antimonium 5 for our rubidium 2, antimonium, and chlorine 6. So what that we want to see is if we can open and we can make rubidium terminated slab, antimonium terminated slab, and see if this confinement can make a different outcome. So this was actually that the central hypothesis that we would like to confirm today. So to do this, actually, there is a workflow approach that we have used. Specifically, we worked using building the 2D slabs, actually rubidium terminated and antimonium terminated, from the conventional cell of the rubidium 2 antimonium chloride 6, from 2 to 5 layers, making a necessary vacuum. We run a DFT plus spin orbit coupling. We have validated the model using Bader theory, okay, on the all electron that we have performance from FHIM's code, because one thing for the people that are not computational, Quantum Espresso give you actually is a plane waves code where actually you have only valence and the conductive electron, valence electron, sorry. And in FHIM's is all electron code, so actually is more precise, and it make actually the calculation avoid mistake about the prediction that based on the electron density. We have also performed density DFPT density functional perturbational theory to see the phonons, to see if it's possible to synthesize. We have also performed Born-Oppenheimer molecular dynamics to see if it is also dynamically stable, so it's not only at 0 Kelvin and 0 pressure. And we also looked for the output about the Fermi surface. So we have looked, we checked, and you will understand after why we have checked to look if there were Weyl points, and also we measured CDAC and spin-hole transport. So starting from the system design, actually we have designed this rubidium terminated and this antimonium terminated to look what is the condition to have the best, actually, to have this antimonium 4. Specifically, what we have done, we have used Bader theory to analyze, actually, the Bader charge. The Bader charge is not actually, we have, first of all, computed the Bader charge for the molecules to see the value of the Bader charge of the antimonium, that we know that in this molecule is 3, 4, and 5 in the specific molecule, and we compared with what we have seen for the rubidium terminated. And we got, for the rubidium terminated, a value of antimonium Bader charge that was actually 1.65. That is near to what we have seen from the molecule that we have built before. And actually, when we increase the thickness, we have seen that from 4, 5 layers, okay, there is happened a disproportion. So actually, we got a kind of trend that stabilized at 2, 3 layer rubidium terminated the antimonium 4, and with the increasing of the thickness, restore the disproportion that is seen in the bulk. So specifically, for the people that don't know Bader charge, why they are different, why they are not +3, +4, +5. So when we speak about the formal oxidation state are integers. So, and we assume that idealized electron transfer. So actually that these should be perfect. But when we look for the Bader charge, actually we are looking the electron density as Bader defined like a mathematical function that based on that, if we look the gradient of the density, the product of the gradient of the density respect to the normal will be 0. This will be the point of the zero flash surface that divide our two atomic basin. And we see that the distribution of the electron inside of this atomic basin actually give the charge of your system, so the partial charge. So your system is not considered alone, but inside of the molecule, or inside of the molecule or the crystal. This also Bader theory is now actually used with success, and it can be also from X-ray PD diffraction or X-ray diffraction. When you can get the electron density, you can compute on the experimental electron density. And we see that are not different from the computed electron density. So actually it's very useful, powerful, and describe your atom like no more like a sphere, but that is deformated inside of the molecule that, or the crystal that play. So the thickness drive actually the stabilization of our antimonium 4. We see that antimonium 4 actually is stable for, I spoke about rubidium terminated because rubidium terminated also, as we will see, is the most interesting by the analysis of the Kohn-Shahn electronic band structure. But the same behavior happen also in the antimonium terminated. So we have 2 and 3 layers that we see the antimonium 4. And when we start 4 and 5 and we go to the bulk-like, this was also done to show that the theory is correct. So that we go to the disproportion limit. So at the end, as you increase the layers, you will go to the bulk, and the bulk, there is this disproportion, as shown by the Mossauer effect. So the first result that we got was that this structure, when we have B layer and 3 layer, we have this antimonium 4 stabilized. The most interesting for us is actually the B layer, because the B layer actually is the most thin device that we could be able to produce. But to be sure that that experimental people could synthesize, we have to look at the stability of the B layer. And specifically, we look at, first of all, on the phonon calculation, to see actually if there are no optical, because you see that here are the acoustic branch that usually are 3. And these are actually, most of the time, they are 0 at gamma and they increase. The all other are the optical branch that describe actually the perturbation between the atom inside of the crystal. The acoustic branch describe the perturbation of the lattice. What we have seen is that when there are no optical branch negative, like in this case, we can say that the structure is stable. So actually it's thermodynamically stable. But this is not enough, because we know that also if the perovskite, we know from experiment that they are easy to be synthesized, we have to be sure that they will resist with the temperature, so that they will not be degraded. So what we have performed was Born-Oppenheimer molecular dynamics, where we increased the temperature for some picosecond, and we look at actually how the potential energy change, and actually how the root mean square deviation of the atomic position change with time. And what we have seen that our B layer is also dynamically stable, because 300 Kelvin, so a room temperature, people can be able to synthesize and get this structure stable, so that will not degrade. So say that we have now an interesting compound, B layer, thin, that actually can be electronically interesting, and look at the transport, electronic transport. Specifically, as I mentioned before, we chose the rubidium terminated specifically for this kind of electronic structure close to the Fermi level. What we have seen is actually that, as you see here, I have not the point, but I think that you look at X and close to M, okay, for the panel A, that is the B layer, we see that it seems that the conductivity band and the valence band, they touch each other. At the beginning, we were thinking that we have found a vial semi-metal. But the analysis that we have performed actually disconfirmed this. So actually, it's simply it's kind of a nodal line semi-metal, where the conductivity band and valence band, they touch each other. The same but more complicated we have seen in the 3 layer, and actually the 4 and 5, due to the disproportion, actually they start to look much more to the same band structure that we see for the bulk, so they are not more interesting, and it is this is called spaghetti likes, that actually is meaningless at all. So in detail, what we have done, so this is the three-dimensional valence band and conductivity band in K-space that have this specific egg shape. Actually, we see that from X to M, we see that they are very close, they are connected each other and are very close to the Fermi level. And we see that most of these come from at the Fermi level, from the chlorine and antimonium. So actually, from the projected density of state. The projected density of state is when we take our Kohn-Sham band structure and we project into the atomic orbital to understand which is the atomic contribution of which orbital at the density of state. And we see that is dominated by the chlorine and antimonium. So these are the two. And for a kind of covalent bond that we see from antimonium and chlorine is also reasonable, that actually they are the game changer. So here we can see that due to this particular band structure, we expect different electronic particular actually thermoelectric properties and also spinol response. So looking most into detail about the Fermi surface, these are the Fermi surface inside of the this red is the conductive band minimum, and the orange is the valence band maximum that you see here. Actually, the Fermi surface is like a map in a K-space that, or this is the Brillouin zone of our B layer, so that increasing of the electron volt, we see a changing. So actually, tell me when it is red, close to the Fermi surface, the Fermi surface is red, so this tell me that I have n-type conduction. When I see that I change the, I increase, so I'm going far from the energy Fermi, like in this, in the third case, actually see the appearing of the orange. So in this case, actually I have a p-type and n-type conduction that are the same point. So actually it means that depending on how I transfer electricity, I can have at the same time p-type and n-type. That this is also interesting because have a compound that directionally change the direction where the current goes, change to be a p-type or n-type semiconductor is something that is can be very interesting. Another, the CDAC actually, that we coefficient that we have measured, is also an interesting descriptor because it measures the voltage generated by temperature gradient. So in this way, we see that when we change the temperature, okay, we see that the CDAC close to the Fermi actually change also the sign, so going from positive to negative. Specifically, this we see when we change the carrier concentration. And to be clear, when we have a CDAC that is more than 0, actually we have a hole. And when we have a CDAC less than 0, we have electron actually thermoelectric. In this case, actually, I'm honest with you that the CDAC coefficient that was found is very low. Usually, to be a good thermoelectric, we should find much more high. We should be actually maintain close to the room temperature, not go to like this, but be in the order of 30 or minus 30. In this case, we simply see that at 300 Kelvin, close to room temperature, there is, okay, a changing of sign that can allow me to make a tuning of this thermal power. But this compound is not, I tell you, efficient thermoelectric. And this is also reasonable because when you have a flat Fermi surface, we are not supposed to find a very good thermoelectric. But we have measured and we have verified this. The spinol effect is another story because actually when we speak about spinol effect, we will see that actually when we change, we have spin orbit coupling to recall the previous slide. Actually, we split the electronic current that pass in a spin up age and a spin down age. And what we have found here was a quite high spinol conductivity that was in the order of the other, for the B layer of the rubidium terminated, of other previous compounds seen in literature. And the most in detail, our result was actually to look, come from the Berry phase, that the Berry phase actually, if we think that we have electron, okay, the electron is also a wave and it moves in the crystal like. And this crystal actually, this movement actually can actually move differently. And with the Berry phase actually give me the movement of this electron inside of the material, inside specifically of the K space. So the electronic geometry can separate spin direction sideways, and this is important to remember. Specifically, what we have found, the last result that was the most interesting for us was that if we have this high spinol conductivity that is in the order of the other compound that are previously seen in literature, make this two-dimensional spintronic material that actually work with the whole doping of gating, that if we go below the chemical potential start to be below zero, actually we get an opposite signal and we have a transmission of spinol conductivity. And this is actually interesting because you think that we studied this complex material and we saw that very thin can 2D rubidio terminated can stabilize antimonium 4 and be a very good spinol conductor. And specifically, the broad implication and testable. So I will be like to see that some experimenters will try to synthesize these, and we try to measure what we have actually simply described computationally. Actually, all these kind of materials, spinol conductivity, it's important because we have, for example, solid state memory and all other electronic device there could be useful for them to have this kind of conductivity. And this work is published in ACS Nano in 2025, last year, and I'm open for eventual question. So thank you for your listening.
Thank you, Christian. Very interesting talk. The talk is open for questions, comments. Just unmute yourself and speak up, or put your comment or question in chat. Raise your hand.
Hello, I have a quick questions. The talk was very interesting. Like, how do you distinguish between the Bader charge and quantum meshes also gives the load-in charges?
What you told me? Bader charge?
Bader charge and the load-in charges, population analysis from quantum mesh ratio.
How I got, or how
No, what is the difference between the two methods of the charge analysis?
Actually, the Bader works on the electron density that you have computed or that come from the experiment. Bader charge can be completely wrong as can be completely right, depending only on the electron density. So it's important that, for example, if you use a wrong description of, imagine that you have strong correlated materials. You didn't use Hubbard approximation. You got a completely wrong electron density, and your result will be wrong. So this is more. This is very sensible Bader charge. The loading is actually a different partition. I'm not familiar with that because I was working most of Bader charge, and because specifically Bader charge I see much more fit into the experiment when I also see X-ray diffraction and I see the distribution of the electron density. That is much more fit for me for the experiment in this way.
Thank
So
you.
most of, I have to tell you that any partition can be used with all the drawbacks, because actually I'm not telling you don't use loading, don't use, so I'm not fanatic in Bader or something like that, depending of the usage that you want. If you want to be sharp to understand the oxidation state, Bader charge is the most accurate at the moment, I can tell you, because consider the atomic basin not like a sphere, but inside and affected by the environment and the chemistry of also of the other atoms.
Thank you.
I have a question.
Thank you very much. Yeah, Urshan, go ahead.
Yeah, you mentioned the antimony MESBAR spectroscopy results.
Yes.
Can you comment on the relationship between Bader charge and isomer shifts observed in the MESBAR effect?
I cannot comment because actually we have looked at the Mossauber effect by the paper that was published some years ago about it, confirmed that there is the disproportion, but and they saw antimonium 3 and antimonium 4, antimonium 5. In our cases, actually, we have no. It will be nice if someone will synthesize and we measure the Mossauer for the B layer, and then we can compare. But at the moment, I cannot compare the Mossauer experiment with the Bader charge because they are different, and we simply wanted the when we have, because I found few papers about the antimonium 4. One was also written only in Russian and was in the Russian Academy of Science when I was there. And actually, I found other papers, but it was a very long time ago. What that I saw more new and very strong paper was the Mossauer effect on the disproportion. But I cannot connect with the Bader because are different experiments. So one is electron density to make this Bader partition and get the charge. The other one was about the peak seen from the Mossauer experiment that showed that we have two different states that I make like a sketch picture. I remember here that when I got, where is, second, was here. So actually they see two local valence fingerprint for the Mossauer spectroscopy. So I'm sorry I cannot connect.
Thank you.
Thanks. In your
I
slide
have a
on,
questions.
yeah, oh, go ahead, Sabri.
Oh, Sabri, hello.
Hi, Kristen.
He's my colleague.
Good to see you. Yes, yes. It was very nice talk. So I just want to ask you about the semi-metal behavior that you mentioned. It's yeah, and you mentioned it's a nodal line semi-metal. Is
Yes.
it correct?
Yes.
So how did you determine its nodal line? Did you run some analysis like symmetry, or you calculate
Yes,
along
yes. We
different
used
path of K-match?
Yes, we used the power flow to get actually the time binding Hamiltonian. And after that, we have started to search actually the topology and the chirality, because if it was a whale point, we should assume to have a chiral point, and the 2 points should have actually because in case we have whale points, the sum of the chirality should be 0 in the material, so we should be 1 plus 1 or plus 2, and the other plus 1 minus 2. So actually, we run this kind of topologies analysis. Because actually, we at the beginning we
Okay,
were
thank you.
excited about the idea to have a whale semi-metal, but unfortunately, it was not like that because it's much more cool whale
Okay.
semi-metal.
Yes. Yeah, thank you.
Thanks.
Can I have a question?
Christoph, yes, go ahead.
Yes.
I can imagine that with modern electrochemical methods, you should be able to get this kind of B or multi-layer systems, and with photoelectron spectroscopy or UPS spectroscopy, you should be getting density of states close to the Fermi level. Do you see any, have you tried to perform this kind of experiments, and do you see any, if yes, do you see any correlation between your results and experimental results from this kind of techniques?
Actually, if we speak in general, these the results that you get with the actually going to detail, we have no performed this experiment. We have at the moment we were not in when we have performed this work, we were not in contact with the experimentalist, and we could not perform this. But it will be nice in the future if someone will be able. If someone would like to do, because it is a good feedback. And I think that speaking in general, when you get these results, experimental results, they actually, there is a literature in the last decades about that from experiment to the Bader charge, you can get actually very close results. So I expect that if you will perform the experiment and we will be successful to get a stable actually B layer, we should measure actually a kind of we should get antimonium 4.
Yeah, of course, experimentally, especially in the case of, say, three-dimensional systems, it's relatively easy to get quantitative electron density distribution and
Yes.
and then perform any partitioning scheme leading either to Bader or to Loveday or
Yes,
to
yes, there is a code.
possible charges. So the question is, I personally wouldn't. I mean, we do this kind of work, but I do not see special reasons for Bader charges. They are as useful as only when you can correlate them with variation of some other parameters. If you find relations between Bader charges and of course electron density goes through zero gradient of electron density hypersurfaces, so they are very sensitive. But I agree that that atomic basins are how to say, are far better objects than a polyhedral representation of B layers or three-dimensional crystals, because in atomic basins you have electron density associated with given atom ion, whereas in polyhedral representation you have simply very complex fragments of electron density of the central atom and the corner atoms. So, I think that atomic basins have certain future in crystallography, mineralogy, material science, and other fields. But that's my comment only.
Yes, I agree. There are. I remember that my supervisor during the master degree, Carlo Gatti, he worked with Bader, and actually I remember that most of the last decades of his career was actually show that there was this correlation between what experimentalists do, and specifically also he developed the source function that was the possibility to understand which atoms contribute to the chemical bonding.
Yeah,
Looking
we have invited Carlo to our webinars in quantum crystallography and related fields. So if you want to listen to his lecture, this will be, let me advertise this, Russell.
Yes, yes. Thank you so
this
much.
will be on 11th of June, 4 p.m. Central European Time.
Okay.
And Carlo will be talking about source function. Thank you very much.
Yes, yes. I was his student. I also made some develop on the source function, make volumetrical source function for the van der Waals interaction. Because actually one of the problem that we have faced was that when we consider the van der Waals interaction, we have no more critical point, but we have introduced the concept of volume critical. So actually with the reduced density gradient, you can actually describe the entire volume of your van der Waals interaction, and then actually understand which atom contribute to this van der Waals interaction. That is very useful, specifically in biological chemistry, that where van der Waals play a big role, and DNA and so on. So actually,
so only the Casimir effect is waiting for nice description.
Yeah, thank you very much.
Thank you.
Thank you.
Anmol had a question.
Yes.
Would you like to ask it, or you want me to read it, Anmol?
Could you please mention again the name of the method used for the topology analysis? Yes, I used the zeta 2 pack, power flow, to generate the tie banding at the Hamiltonian. I use this because there are two possibilities. Or use the localized Vannier function, but actually they are very sensitive to the energy window that you use, and or you use actually the projected atomic orbital, and you use this code called power flow, where this projected atomic orbital you take and get your time banding Hamiltonian. At the end, they converge to the same results, but it's much more easy to use the projected atomic orbital. And after that, I used zeta 2 pack to look the topology, to look if it was a Weyl semi-metal or not. There is Hussam.
Thank you. It was really nice talk.
Thank you.
So we've had questions from at least 7 different countries so far. Hussam.
Thanks, Russ. Great talk. Something I was thinking about, maybe it's relevant, but I think a lot in terms of X-ray diffraction sometimes. So I was just wondering if the disproportionated phases are uniquely on or are distinct crystallographical sites than, say, antimony 4. In other words, will we see difference in X-ray diffraction between these?
I think that the time of the disproportion is so fast that you will not see you will see any distortion that you expect in the X-ray diffraction. It's actually because it's like when you see for example, there are cobaltites that actually you see that cobalt can be 3 and 2, and you see that actually there is it's too fast this electron that move that the X-ray cannot catch. And you see like a medium structure that is actually with all the chemical, the distance between the atoms that describe your chemical bond like identically.
Understood. Thank you.
Because actually we got the structure from, I forgot to tell that the structure was got from experiment, so from previous experiments. So actually people that have done this experiment, so we see that when you catch the structure, all the antimonium look the same, but it's impossible because impossible. The Mossauer show that is not like the case, but in the crystallographic results show that they are identical.
Could I ask a question again, please?
Yes.
Go ahead.
Yes. In the case of the two-layer, or when you have antimony, say 4, I understand it's the band structure, but do you think the orbitals that are involved in the bonding is in the XY plane? And when you go to the 3, 4, 5, also XZ and YZ planes now, the orbitals in those also start interacting. So there is some sort of for a lack of better term, some chemical pressure that is localizing the interaction to just XY plane when you have 1 or 2 layers. But when you go to 3, 4, also the XZ and YZ plane orbitals take over. Just a thought. I could be wrong, but a question.
Actually, increasing the number of layers, we see that the environment, so actually the atoms surrounding the antimonium actually and the atoms that are close to the surface act like the difference. So this maybe also we can, all the orbitals actually, if we have a B layer, but the orbitals of each atom are orientated in the three-dimensional space. So actually, I think that the effect of the moving from a 2D moving to the 3D, this change the confinement and this change actually the chemist. But remember that our system is three-dimensional, so in the space you have always these orbitals, if I correctly understood your question. So because most of the confinement from 3D to 2D change the quantization of the system reacts differently, and actually the wave function are also different orientated. And also if we speak like a chemist, that we think that we have this beautiful orbital that is the radial part, that is the angular part of the wave function, the real part of the angular function that are distributed along, they are always three-dimensional. So I don't know about pressure or something like that, because at the moment we have no applied pressure.
No, yes.
Yes.
Thank you.
Yes. Because if you want to see about pressure when we have applied, you can go to the work that we have published in 2021 about silicene, that actually there we have saw a different changing of the hybridization of silicene from sp3 to sp3d, and actually we got these kind of different electronic properties, and then there it was interesting also this.
Yeah, the reason I mentioned that is I'm actually referring to Professor Rolf Hoffman, who sort of suggests that there is things like chemical pressure. I mean, this is not an external pressure, but just the matter of being electrons in certain thing exerts certain pressure, and that's why you have chemical reactions and things like that. So, but anyway, very interesting talk. Thank you.
I have to think about this. I have to, because I read the new book of Roald, but I didn't get this. So, okay, I will think about that.
Okay, well, thank you very much for all the questions. Clearly, there's a lot of interest in this material and in your work, Christian. I have some comments and questions, but I'll talk to you offline. So we're at the top of the hour. Thank you very much for joining us, and thanks again to everybody for being a part of this. Okay, stay in touch.
Thank you.
Bye-bye.